So in order to be able to state this very remarkable remark as a proper theorem, we need to understand what we mean by similar in a precise way. And we will make the term similar precise in two ways. And each of these ways will give us a different geometric way to look at graphs. Let's look at the first reasonable definition of similarity. The idea of this definition is you consider two graphs to be similar if the only difference between them is that you have a bunch of vertices that do not cause edges to branch. What do I mean by this? Look, for example, at the following two graphs. And so this is one graph, and the other graph looks like this. So these graphs are not isomorphic. For one thing, they have a different number of vertices. But these vertices, the two vertices here and the three vertices here, don't really do much for the structure of the graph. If you look at this graph from far away, you probably won't even see them. Geometrically, they look very similar. So how do we make this precise? Well, the precise notion is that of being homeomorphic. Not homomorphic, but homeomorphic. So two graphs are called homeomorphic to each other if they can be obtained from the same graph by inserting vertices of degree 2 on the edges. So let's look at these graphs. Well, both of these graphs can be obtained from this graph. They're sort of common ancestors, so to speak. In one case, I added extra vertices of degree 2 on this edge, and in the other I added a different number of vertices of degree 2 on the other edge. And the idea is that adding vertices of degree 2, this just basically means you put a vertex in the middle of an edge. It doesn't create any extra branches. It doesn't do anything to the geometric structure of the graph. So two graphs are called homeomorphic if there is one sort of common graph that becomes one of them if you put these degree 2 vertices somewhere, and the other if you put them somewhere else. And the interesting thing is that this doesn't affect planarity much. So look at this graph, for example. What I did was I took K5 and I added a couple of blue degree 2 vertices in the middle of some edges. Clearly, this graph is non-planar. You can use the exact proof that we did for K5 with trying to move the edges around, carrying along these vertices. Adding these vertices doesn't make the graph more planar than K5 was. So now we can state the first version of the remarkable remark as a theorem. This theorem is due to Kazimierz Koratowski from 1930. And the theorem says that a graph is planar if and only if it contains no subgraph homeomorphic to K5 or K33. So if I have a graph that, say, looks like this, then it has a subgraph, that this black and blue subgraph, and this subgraph is not isomorphic to K5, but it's homeomorphic to K5. And so I know that my whole graph is not planar. The second way to define what we mean by similar will rely on contractions. So in this different way to view things, we will consider two graphs similar if you can deform one of them to the other by contracting some edges. So for example, if we have this graph, well, if I contract this edge, so if this edge is E and this graph is G, I look at G contraction E. Remember, this means that I delete E and glue together the end vertices, so it looks like that. Well, they might not look very similar, but really all they are is somehow a circle. One of them has 3 vertices, one of them has 4 vertices. So it's a similar idea that you have some sort of geometric similarity. The proper definition of contractibility is the following. So you call a graph G contractible to a graph H if H can be obtained from G by successive contraction of edges. And note that this is not a symmetric relation. If I can contract G to H, this doesn't mean I can contract H to G. Let's look at some examples. So the complete bipartite graph K1S is contractible to the null graph on one vertex. Why is that? Well, K1X, let's look at K13. It looks like this. So I start by contracting this edge, then I get something like this. Then maybe I contract this edge, I get something like this. And then I contract the last and final edge, and I get the null graph. Obviously, I could not have started from the null graph and contracted anything to get K13 back, but I can contract K13 to N1. And in a similar way, any tree can be contractible to the null graph on one vertex. Just start with the edges that go to the leaves and contract them, and keep doing that until you just have nothing left but one vertex. Do that as an exercise. A more general statement, if you have 2 homeomorphic graphs, then they will be contractible to the same graph. It's not necessarily a more general statement, but a different statement. So why is that? Well, if I have my 2 homeomorphic graphs, so let's look at our old friends, this one and this one, and say this one has 2 vertices here and this one has 3 vertices here. Well, if I contract this edge between the 2 vertices, I will end up with just one vertex. And then I contract this edge with the one vertex, and I will get this vertex disappearing altogether, and I'll get back the red graph that I started with, the sort of ancestor graph. And same thing here. So I can always contract 2 homeomorphic graphs to their common ancestor, so to speak, so they are contractible to the same graph. The Peterson graph is contractible to K5. How does that look? This is the Peterson graph, and then you see if I contract my intermediate edges, I will basically glue together each vertex of the pentagon with the corresponding vertex of the pentagram. And then I will precisely get the K5 graph, which now I have very artistically drawn like that. So what does this tell us about the Peterson graph? Well, it might be harder to see than with homeomorphism, but you might be able to still believe me if I would tell you that in a similar way that we did with K5, you can prove that the Peterson graph is non-planar. And the problem, so to speak, will come from this similarity to K5. So the Peterson graph is non-planar just because the K5-ishness of it is non-planar. That sounds horribly non-scientific. What's the proper formulation? It is the following analog of Kuratowski's theorem, that a graph is planar if and only if it contains no subgraph contractible to K5 or K33. So if you have a huge graph that has the Peterson graph as a subgraph, then it has a subgraph that is contractible to K5 and therefore is non-planar. So now we have these 2 geometric notions, contractibility and homeomorphism, and the conclusions are strikingly similar. So whichever notion you prefer to use, look at a graph and look for subgraphs that are similar, either in terms of homeomorphic or in terms of contractible, to K5 or K33. So if you find any, then the graph is non-planar. And if you don't find any, then the graph is planar.